So a lot of people have troubles with this concept. And what we have is we have a harmonic wave that has a form of kx, or sine of kx minus omega t minus phi. So it has some position, some time, and some phase shift. And it says that a is equal to 1 meter, k has units of inverse meters, omega has units of inverse seconds, and phi has units of radians. And it has the plot of this graph. And we want to know which function best describes this diagram. Well, I'm going to look at this thing and say, I'm only given time information. So the best that I can do, so if I give in time information, that means that I have no knowledge of how omega changes when time, or what omega is as time changes. So omega is going to tell us how this thing evolves in time. As time gets larger and larger and larger, it tells us how fast these points oscillate back and down. So this point right here is going to eventually move down and back up as we flip through it. So we're looking at the first page of one of those nice little flip books where you can see the little man run across the, I don't know, little flip books that you get where they show you each one little picture. We're looking at the very first picture. We don't know what happens to omega because we don't have the rest of the little book. And they already gave us a. So I'm going to look at this and I'm going to see that I have y is equal to a sine of kx minus omega t minus phi. And what I'm going to look at in this is that I'm given a position, right? I'm given a position versus position graph. So I'm looking up and saying this thing goes between a and minus a, because this is measuring in units of a meters. And I'm going to see, or it's measuring in units of meters. So I see that it already has the right amplitude. So that guy's okay. I already said this one's okay. But this graph right here says it tells me as I move in position how this thing changes. And I'm going to look at a couple points here. And I'm going to see that right here, this point right there, and this point right there, that the distance between the two, we're just a little bit on the downside, so we go down, up, and a little bit back down, so I repeat myself. So this is one wavelength. So I know that one wavelength is equal to 2 pi over k, k being our wave number, and k being this value right here. And I know that this value right here, this lambda, is equal to 20, it goes 10, 15, 20, 25. It's equal to 15 meters. So that means k is equal to 2 pi over 15 meters. So I can rewrite my equation. Y is equal to a sine of 2 pi over 15 meters x minus omega t minus phi. And I'm not done yet because I don't know what phi is. And phi is actually a little bit of a tricky thing. So I can see that my sine function, I know what a sine function looks like. If I were to plug this in to be just minus kx or plus kx minus omega t with no phi, that means I would know that this graph would have to start right there. Because at zero position, at zero time, I have to start at 0. Because sine of 0 would be 0. But I don't. I see that I am shifted a little bit over. So I still start with the up, down, but I started a little bit in. So I need to figure out, and this is what the phase shift is. So that is my phase shift. And it's not the actual phase shift because the phase shift has units of radians. This has units of meters. So I need to figure out really how much of the cycle have I gone through. Well, I can see that this distance right there, this distance right there, and that distance right there, these are all the same length. And this is actually, if I look, I see that this point right there is the same thing. So I see that this is, again, 1 lambda. So I have shifted by 1/3 of a cycle. Right? I have 3 equal increments in one, and I started with a shift of 1 of these increments. So I look and I see I shifted by 10 meters, or by 5 meters. 5 meters is a half of a cycle, or half of a wavelength, half of my cycle, which happens to be 2 pi over 3 radians. That is a 1/3, not half of a cycle, 1/3 of a cycle. 1/3 of 2 pi radians will tell me how many radians I get. This is what I call phi. So my final equation that I get is equal to a sine of 2 pi over 15 meters times x minus omega t. Couldn't figure out anything about that. But I also know that I have a 2 pi over 3 as my phase shift. And if I want to check this, I can plug in a 0 for x, a 0 for t, put myself at this point right there, and see if I get the sign to be in this point. So minus 2/3 puts me somewhere down over here. Another one I could check was I could check 5 meters. And if I check 5 meters at 0 time, 5 meters at 0 time would give me 2 pi over 3, 0 time here, and a minus 2 pi over 3, which would give me a sine of 0, which would be 0. So I've checked a couple points just to make sure. I personally like to check my phase shifts because I always get this sign the wrong direction. Just to check to make sure, I'll check 2 points to make sure that they look right. But all we did was just looked at, figure out what this graph tells us. It gives us some information about its position as a function of time, so we could get its wavelength. And we know that initial conditions, where it starts at time equals 0, at a position equals 0, we know we have to shift the sine function to be in the right location for it, so we have the right graph. So nothing too terribly difficult, it just takes a little bit of time to get through everything.